Hi and welcome to section 5. This section comes with videos dedicated to highlight some approaches meant to reduce or eliminate data loss between collection, analysis and message queuing tier. In this video, we will discuss about the hybrid message logging concept, which can be useful in order to increase fault tolerance in our streaming pipeline. The agenda of this video was written in such way to provide all the needed information and architectural headlines needed to implement a hybrid message logging solution. At the end, we will write a complete implementation via Spring Reactive and MongoDB. Let's begin with a dissertation meant to highlight the differences between the two primary approaches for implementing fault tolerance: checkpointing and logging. Both of them, checkpointing and logging, are designed to protect against data loss and enable quick recovery of the crashed nodes. Checkpointing has a significant number of implementations, but mainly any such implementation relies on global snapshots and is prone to data loss. The system is recoverable up to the most recent recorded global state, so there is a gap between states where data can still be lost. In other words, a global snapshot represents a global state of a streaming pipeline that is prone to data loss if we cannot capture the global state every time data is updated in the system. For example, think to the autosave feature existing in Google Docs, where we can recover a document from the last checkpoint, which is not always the last editing. These gaps causes checkpointing to not be the best choice in a streaming pipeline, since there are many technologies and tiers involved. In addition, some tiers as Spark and Kafka may provide fault-tolerant mechanisms. Now, trying to overcome the checkpointing issues and provide the ability to recover up to the last message received before a crash, we turn our attention to the logging techniques. The main idea of logging is that each tier in the streaming pipeline will save each message to a stable storage before performing any action on it. In other words, each tier in the streaming pipeline independently records all messages it receives and plays them back after a crash. This technique is known as receiver-based message logging, or shortly RBML. But this is just half of the job. It protects the current tier, but it doesn't help us in case that the next tier crashes or we need to face a network interruption. And here is where the sender-based message logging technique, or shortly SBML, comes into play. Mainly, this technique involves writing the message to the stable storage before it is sent. When we combine these two logging techniques, we say that we are using hybrid logging message, or shortly HML. But for now, let's identify some points of losing data in our streaming pipeline. So here we have isolated a part of our blueprint architecture, more precisely the collection and the message queuing tiers. We may consider that an RSVP is safe or not prone to be lost in the meetup RSVP's endpoint and in the message queuing tier, but we cannot say the same thing while an RSVP is traveling between these points. For example, an RSVP can be lost while is received in the collection tier, or when we send it to the message queuing tier, or inside the collection tier during some specific business logic. So we have identified 3 points of losing data, but how we can deal with this problem? Well, we can rely on receiver-based logging message to write every received RSVP to the stable storage before performing any action on it. And we can rely on sender-based logging message to write each RSVP in the stable storage right before we send it to the message queuing tier. This is the RSVP that was processed by the collection tier business logic, so it may not be the same as the received RSVP. If we apply both the logging techniques, then we can refer to them as hybrid message logging. Okay, now let's focus only on the receiver-based logging message architecture. We will rely on two suggestive diagrams meant to highlight the place of RBML in the collection tier. First, we will cover the happy path with no failures, so let's see how data is flowing through RBML. So we have a stream and the collection and message queuing tiers. The collection tier contains a stable storage, some business logic represented by the node logic component, and the RBML logger. At first step, a message is sent from a data producer. For example, the meetup RSVP endpoint is sending an RSVP. The message hits the RBML logger as the entry point in the collection tier. So the RBML logger gets the message from the data producer. Further, the RBML logger sends the message to the stable storage, so the message is written to this storage. Notice that so far no action was taken on this message. It was written to the storage as fast as possible. Now that the message was saved, it can be passed to the collection tier business logic. The business logic is optional, but when it is present, it usually consists in filtering, enriching, or routing the data. Finally, the message is sent to the message queuing tier, the next tier in the streaming pipeline. And this is the end of the happy path. Now let's focus on recovering the data via RBML in case of a failure. In other words, the load balancer that sits behind the collection tier cluster will stop sending messages to this collection node. Next, we focus on the messages from the storage that has not been processed. The RBML job is to read these messages from the stable storage and send them to the node logic. Each processed message is sent to the message queuing tier. After all the pending messages are processed, the node is considered restored and can be put back into the load balancer list. This means that we are back to the happy path. Okay, now let's focus on the flow specific to the sender-based logging message. Let's follow the same scenario. For start, let's see the data flow through SBML in case of the happy path. So we have a stream and the collection and message queuing tiers. The collection tier contains a stable storage, some business logic represented by the node logic component, and the SBML logger. At first step, a message is sent from a data producer. For example, the meetup RSVP endpoint is sending an RSVP. Each message hits the node logic of the collection tier, so the collection tier processes the received message as fast as possible. The processed message is sent to the SBML logger. This message can be exactly the received one or a modified version of that one. The SBML logger will send this message to the stable storage, so the message will be persisted in this storage. After the message was successfully saved in the stable storage, the SBML logger will send it to the message queuing tier. Further, the SBML logger waits for an acknowledgement from the message queuing tier that the message was received successfully and is safe. With this acknowledgement in hand, we can mark the message as replayed, or delete it from the stable storage since we no longer need it during recovery. In case of technologies such as Kafka, we can rely on acknowledgements, while in the cases where the message queuing tier technology is not capable to send an acknowledgement, we need to mark as replayed or delete the message from the stable storage if no error occurs when sending the message. Well, this is the end of the happy path. Now let's focus on recover the data via SBML in case of a failure. In other words, the load balancer that sits behind the collection tier cluster will stop sending messages to this collection node. Next, we focus on the messages from the storage that has not been sent to the message queuing tier. The SBML job is to read these messages from the stable storage and send them to the message queuing tier. For each message, the SBML logger waits for an acknowledgement from the message queuing tier that confirms that the message was successfully received. When an acknowledgement is received, the SBML logger marks as replayed or deletes the corresponding message from the storage. After all the pending messages are processed, the node is considered restored and can be put back into the load balancer list. This means that we are back to the happy path. Now let's combine the RBML and SBML architectures in a single architecture under the hybrid message logging. But why we should care about hybrid message logging if we are implementing both RBML and SBML? Well, consider this. If we go with this approach, then we are writing to the storage at least twice during a normal execution. This has a significant performance penalty, and if we check this sketch, looks like our collection tier does more logging than processing. But if we take the best from RBML and SBML, then their powers combined is the best choice. So let's see how hybrid message logging extract the best from RBML and SBML by taking a step-by-step data flow. So let's assume that a new message is ingested by the collection tier. This message is received by the RBML logger and is sent and written asynchronous to the storage. Notice that writing to the storage asynchronously comes with a negative impact in complexity of implementation and a positive impact in performance. The complexity comes from error handling, while the performance comes from a multi-core processing capacity. Well, the rest of the data flow should be routine by now. The message is passed through the business logic and the processed message hits the SBML logger. This is responsible to send the processed message to the message queuing tier and to wait for the acknowledgement. Finally, it deletes the message from the storage. If the messages are written asynchronously to the storage, then at this step you need to ensure that you don't try to delete something that was not inserted yet. But in order to avoid these kind of issues, in the example that follows, we will insert in a synchronous fashion. Since we use Spring Reactive and MongoDB Reactive support, it will be a piece of cake to switch to asynchronous inserts and challenge yourself to deal with the possible issues. Before we see a possible implementation of hybrid message logging, let's see some implementation hints. So we will implement an approach of hybrid message logging in our collection tier. Our implementation will have the following key points. Processing new RSVPs and recovering RSVPs will happen asynchronous. This means that while we'll recover data, we will ingest new data as well. We not follow the classical approach of suspending ingestion during recovering data. New RSVPs are inserted in the storage in a synchronous fashion. This means that we will not proceed with business logic until the RSVP is saved in the database. We wait for Kafka to send an acknowledgement for each RSVP before we delete it from the database. This means that the collection tier becomes a synchronous producer. As technologies, we will rely on Spring Reactive and MongoDB. Okay, so let's see a possible implementation of hybrid message logging via Spring Reactive and MongoDB. Okay, let's start with this simple class RSVP document. Each collected RSVP will be mapped into an instance of this class with a long ID representing the timestamp, the RSVP content as the data field, and the status, which can be pending, processed, unsent, or failed. This class is needed to map RSVPs between Java and MongoDB documents stored in the temp RSVPs collection. Further, we need some tiny adjustments in two classes that you already know. First, let's focus on the RSVP's Kafka Producer class, more precisely on the sendRSVP message method. We use this method to send an RSVP content to meetup topic in Kafka. By default, the send method is asynchronous, but we need to wait for an acknowledgement before we delete the sent RSVP from the storage. In this context, we can set the producer as synchronous via this configuration. Further, the send method will block until it receives an acknowledgement or it passes a timeout of 30 seconds. In case of timeout, an exception will occur. We catch this exception and we mark the current RSVP as unsent if this is the first time when we try to send this RSVP. But if this is a replayed RSVP, then it already has been marked as failed in the database, so there is no action needed. If no exception occurred, then we mark this RSVP as processed. Okay, now let's focus on the handle message method. Remember that this is the method that handles each message received from the meetup RSVP's WebSocket endpoint. Now, instead of sending the message to Kafka, we pass it through the hybrid message logging handler. More precisely, we pass it to the handle new RSVP method. Okay, let's see the hybrid message handler implementation and let's start with the happy path. This means that an RSVP is saved in the database, is processed, which means that is passed through our business logic, is sent to Kafka, and is deleted from the database after the acknowledgement is received. First, each RSVP hits the handle new RSVP method, which takes the RSVP and creates an instance of RSVP document from it. We attach a timestamp ID, we mark the status of the RSVP as in pending, and we wrap it in a Java list with a single element. But in the future, you may decide to insert in batches and add more RSVPs in this Java list. For example, if the stream speed will increase to, let's say, 100 RSVPs per second, then inserting batching of 100 elements will be more suitable than using a database connection for each RSVP. Further, it's time to insert this RSVP document in the database. And for this, we call the insert RSVPs method and we pass to it this singleton list. Here, we use the Mongo template to insert the content of the list in MongoDB. This method inserts this list of objects into a MongoDB collection in a single batch write to the database. So if you add more RSVPs in the list, then this code will work as expected and will insert the entire list in a single write operation. Notice that we didn't attach the subscriber because we want to insert in a synchronous fashion. But if we attach a subscriber, then this code becomes asynchronous and the flow will continue without waiting for the insert operation to finish. For now, let's keep it synchronous. Finally, we call the process RSVP method and we pass to it the returned flux, which contains the inserted RSVPs. In this case, a single RSVP. This method is responsible to continue the chain of operations. So after insert, we can pass each RSVP through an optional business logic. In this case, we have just a dummy code, as you can see here. But in other cases, you may need to add some lightweight business logic before sending the message to the message queuing tier. Okay, so after passing through the business logic, it's time to send the RSVP to Kafka. Right before this, I added a delay of 100 milliseconds just to slow down the process a little bit so we can visually inspect it later. But this delay is not required. Further, we send the RSVP to Kafka in the meetup topic. Finally, we attach a subscriber to our chain of operations, and this acts as the trigger that will roll up the insert, business logic, and sending RSVP to Kafka operations. Mainly, we subscribe a Java consumer to this flux that will consume all the elements in the sequence. If Kafka sends an acknowledgement that confirms that the RSVP is in its hands, then we can delete it from the database. But if we get an exception, like a timeout exception, instead of an acknowledgement, then we mark this RSVP as failed in the database. Since there is no need to update the RSVPs that already failed in the past, we check only for the unsent RSVPs, which are at first attempt. In order to delete an RSVP, we use this method. And for update, we use this method. Notice that these two operations are asynchronous. Okay, so far so good. Now let's focus on the sad path, when we need to recover after failure. So, after a failure, when we restart the node, we need to check the database for the unprocessed RSVPs. These are the RSVPs in pending or failed state. We try to take all of them and process. When the application starts, it hits the recover after restart method. This method simply counts the number of records from the database, and if it's greater than 0, then it calls the recover RSVP method. This method queries the database for all records and passes them to the well-known process RSVPs method, which applies the business logic and sends them to Kafka. Okay, while the collection tier is running, there is one more recover mechanism that we use. This is implemented in the internal recover of failures method. This method is scheduled to run at every 10 seconds. It scans the database for RSVPs marked as failed and retries them via the recover failed RSVPs method. We also have here a threshold, which allows us to signal when there are too many failed RSVPs. This can be a sign that we should stop the process for a while. This recover mechanism is useful if internet is down or a Kafka broker is down and the application needs to wait for the rebalancing process. During this time, we collect several failed RSVPs, which will be recovered by this internal mechanism. If the problem persists and the threshold is exceeded, then we need to take an action such as stop ingesting, sending a notification, replay failures, and so on. Finally, the application starting point is in the main method. Notice that we call the recover after restart and do handshake methods via the application runner. So we start the recover process and ingest new RSVPs in an asynchronous fashion. But if this is an issue, then you can easily switch to asynchronous mode and wait for the recover process to finish before starting the ingestion of new RSVPs. Okay, it's time to test the application. I will start the application for the happy path, and I will try to capture an RSVP in MongoDB before it's deleted. So here it is, an RSVP that it is in pending state, and after refresh it is gone. In addition, if we check the Kafka command line consumer, we can see that it receives RSVPs, so it's working pretty good. Okay, let me stop the process, and now let's force a scenario for testing the recover path. First, I will comment this code and run again. Notice that since I have blocked the delete part, we have a bunch of RSVPs in pending state. Now we stop the application, we remove the comments, and we restart it. If everything is working fine, then the MongoDB collection should be depleted by the recover mechanism, and this is exactly what is happening now. Now let's stop the application again and let's see the last scenario. I restart the application, and there is nothing to recover. So it looks good. Now I will stop the Kafka broker. Notice how the RSVPs are collected in the database and starts to have the failed status. The internal recover mechanism tries at every 10 seconds to replay these RSVPs, but with no success, since the Kafka broker is down. Well, I will not wait until the threshold is exceeded, and I will restart the Kafka broker now. Notice how the number of RSVPs starts to drop until we are back on track. So we successfully faced a temporary unavailability of the Kafka broker.